Good afternoon, Math 105 students, and a happy new unit to us. We have just gotten through the second exam of the course, and if you've made it this far, then you are really in for a treat in what remains for the rest of our semester, because we are right now making a turn, a pivot away from talking about the material of the first couple of units in isolation, where we talked in our first unit about sets and how mathematicians use sets and logical reasoning to think about assessing the truth of propositions. And then in our second unit, we talked about modeling the world using algebra and algebraic reasoning and graphs and data. And in our third unit, we're going to wrap all of that together by thinking about a really important topic for our existence both in the workplace and in the world, and that is statistical literacy. How do we use numbers to communicate about statistical phenomena in which there is inherently some uncertainty and some measurement error? If I want to understand the world, I have to come to grips first with the notion that I can only observe a small part of that world. And so statistics, broadly speaking, is about trying to make inferences, to draw conclusions about a set of data and observations and things that is so large that I can't possibly see all of it, and try to make some inferences, reasonable inferences, measured inferences, inferences that have inherent uncertainty to them about that large population, just by studying a small sample that we are able to observe and understand. So that's kind of what statistics is about. And we live in a world today where there is so much data being collected and analyzed on a regular basis by everybody, from nonprofit organizations down to business, down to government, academia. There is more data being collected and analyzed in the world than ever before, because we have more ability now than ever before to store data, computing power to analyze and discover stories out of data. There's a whole field called data science that is growing out of the need in the workforce for there to be trained, skilled employees who understand how to tell a story with data, and maybe more importantly, how to not be misled by a story that's been told with data. Those are the kinds of questions that we want to address, at least at a basic foundational level in our last unit of the course. So that unfolds over the course of the next 5 weeks in a couple of different ways. If you're currently my student in Math 105, here's the plan. The first is that we're going to be introducing, in just a few minutes here, I'm going to be introducing our semester project. This project is going to be the thing that kind of structures, scaffolds our thinking about probability and statistics over the course of the next 5 weeks. And because you and your group are going to be busy working on that project, as I mentioned in an announcement a couple of days ago, we're going to be changing sort of the role that your homework, your online homework plays alongside of your quizzes for the remainder of the semester. Namely, you'll be able to earn equivalent credit to a quiz by completely finishing the homework in a given week. So that's going to be really, I hope that takes some of the pressure off of the quizzes and the homework for you, or maybe shift some of the pressure from the quizzes to the homework, which you had to do anyway, and really can give you some room, hopefully, to focus on the project. So in order to master one of the topics that remains in our course this semester, you can do that by completing the homework and then just getting one more check mark. That check mark can come on a quiz, or it can come on the exam. And the next time you're going to see these topics on an exam is on the final. So it'll be hopefully a little bit lower pressure in finishing the topics for this semester. So the goal of our first session today is going to first of all be to introduce what the project is going to be about. And then second of all, to look at, really, I'm going to try and make it as lively and illuminating as possible, but there's a lot of terminology that goes into how we talk about probabilistic and statistical events. And I want to give kind of a rundown of some of the main language that we're going to have to use. It gets used very specifically in the study of statistics and in mathematics. And the more that you're able to keep that language straight, the better that this material will tend to go for you. So that's kind of the agenda for today. Let me put the agenda up on the screen here. So the first thing I want to do is introduce our project for the semester. It's called the House Hunters Project. And then after that, get into these definitions and terminology around probability. So the main hits that we're going to look at today are words like sample space, event, mutually exclusive, probability, conditional probability. And what I especially am going to want to do is I want to connect the meanings of these words, both to visual representations of them, and also connect them back to the material that we learned way back in unit number 1, which was our unit on set theory. Because really, where set theory is the study of collections of objects, to study probability is really to study how do I compare one set to another. In particular, the question about probability is how much in measurement of a larger set is comprised by a smaller set. So really at its heart, a probability is the result of measuring a subset within a larger set to figure out how much of that larger set is contained in that subset. For example, I could measure, I don't know, the GPAs of every student at Bridgewater, every undergraduate, and get 9,050 different people in my whole population. And that would become my large group, what we call our sample space in probability. And then I might ask, of all 9,050 undergraduates at Bridgewater, how many of them have a GPA over 3.5? Well, that's going to be a subset, isn't it? Because not every undergraduate at BSU is going to have a 3.5 or bigger, but some of them will. And if I find out how many of them are in that group, that gives me a measurement of the size of that set relative to the larger set. So maybe out of the 9,050 BSU students, maybe 5,500 of them have a GPA of 3.5. So the probability of randomly selecting a BSU student and having that person be a part of this small group that has 3.5 GPA or higher is the ratio, the result of dividing 5,500 by 9,050. So it's a comparison of a subset to a larger set that it resides in via a measurement process. And that probability, because it's the result of a ratio, it's a result of a part-to-whole comparison, a division problem, we very often also state those probabilities as percentages along the way. So a lot of the concepts we've been talking about separately in the first couple of units, those are going to come together and really help to underscore our understanding in this last unit when we talk about statistics. So that's the plan. But I'm very excited about what our semester project is going to give us the opportunity to do. So the first thing that I want to do is I want to introduce that project. And for that, I have just this short 2.5-minute teaser video that we'll watch together here in the stream, and then I'll come back together and I'll say a little bit more about sort of my vision for what this project is going to look like. So here's the project teaser.
Hi, I'm Jen. This is my husband Brad, and I work as a wedding planner.
And I work as a stay-at-home husband. I actually just left my job so I can keep things tidy around the house for Jen.
So with our budget, I'm looking for an open concept home in the Beverly Hills / West LA area with new appliances, hardwood throughout. What else do I want? His and her sinks. Oh, and a yoga room facing east for my morning routine. I feel like this is the perfect neighborhood. I really like that one. I could totally picture myself living in there. Do you think it's within budget?
Oh, I'm not sure, sweetie.
Can you imagine how happy I would be every single night when I came home? Just a thought.
My must-haves include a private place for me to
Okay, so we've been approved for $99,500. So there is no excuses that Kim can't find us something perfect. No excuses.
Oh, one second. Okay, I'm good. So we got the house. Really excited. Jen loves it.
Come in. Come on.
So, did we find a good fit?
Oh, I sure did. It's everything I've ever wanted. Wine.
Oh, please.
Really excited. Jen loves it. It's really expensive, but we're gonna make it work. I've been sleeping in my car, not because I'm not allowed to sleep inside or anything, but just because I've been picking up some extra jobs to make a living, selling phone memory cards to people door to door, and been driving Uber and Lyft, and I've been selling some supplements and also some phone books. So if you guys ever need anything, let me know. I can get a coupon code for you, 10% off. But we're really excited for this new life that we're going to be living in California.
Cheers to me. Cheers.
There goes my microphone. So that's the plan for the project, or at least that's a short teaser for a plan for the project. So the real question in the project that I want you and your teams to answer is, what happens when expectations meet reality? Which is too broad of a question. Let me try and whittle that down a little bit. What happens when the expectations that buyers have when going to buy a house and secure a mortgage for that house meet the reality of the income and the assets that they might have to support whether or not they should even be qualified for a mortgage of that size in the first place, right? These are the kinds of questions that have, yes, they have both a business dimension to them as well, because banks and mortgage lenders are making decisions based, again, usually on big amounts of data, on whether or not a buyer is a good credit risk or not to be given a mortgage. But underneath that decision making is some really good mathematics and some really good statistics. And these are the kinds of processes that affect the everyday lives of anybody in the consumer market. I remember when I bought my house in 2010 down in Plymouth, just how consuming of a process that it was to apply for a mortgage, get several different offers. Oh, we could give you this interest rate, or we could do this one if you did a certain down payment, or so on. They did this really invasive look at all of your finances and your assets and your income, pulling your pay stubs and your tax returns and all of that wonderful stuff. And all that stuff goes into a giant meat grinder somewhere. And then out the other end of it comes the bank's recommendation. Oh yeah, we can give you a mortgage at this interest rate. Or, oh no, we don't think that you're worth the credit risk for giving you this mortgage because we don't believe you'll be able to pay it back, right? The mathematics and really honestly the computerized algorithms and the human decision makers that go into these processes affect all of our lives ultimately. All of us are subject to these algorithms and their whims on a regular basis. So this project is meant to give you some experience actually going through the mathematical analysis of whether or not a set of buyers can afford a certain house based on everything that we can learn about them. So what will you be doing over the course of this project? So in the project, the big question that I want you to answer is, can these buyers afford this house? And so actually, the first step I'm going to have you do is I'm going to have you find and watch an episode of House Hunters. So what I'll be doing is I'll be sharing with you some links to resources where you can watch an episode of the HGTV show House Hunters. The idea of the show, of course, if you've ever seen it before, is that they find a realtor to work with a buyer. Usually, very often it's a young couple, sometimes newlyweds or whatever, shopping for a home. And as the viewers of House Hunters, were given a little bit of information about the buyers. The introductory teaser video that I shared with you, which was remixed out of a video that was produced and released by the what's his name, Cam Banfield on YouTube, called Super Cam Vision. I thought it was really well done because it really highlights the absurdity of the show sometimes, because we get a little bit of information about the buyers. What do they do for a living? Oh, I'm a wedding planner. Oh, I'm a stay-at-home husband that takes care of the house. And from that information, usually we start, as viewers, at least I do, to start making some inferences. All right, how much money are they really making in those jobs? I'm a school teacher. I work at Dunkin' Donuts. All right, well, what's their income really probably look like? But even that is a question that would require a lot of speculation to be able to answer, because there are a lot of variables involved in that as well. A school teacher who's been in their job for 10 years is going to be making more money than a school teacher who's only been there for a year or two. Also, geographic location. School teachers in Massachusetts probably make more at an equivalent job with an equivalent amount of experience than, for example, a school teacher in Arkansas. Right? Standard of living is different in different areas. And so your project, after you've watched your episode of House Hunters, the two things that you and your group need to do the most is to find out as much as you can about the buyers. Find out about their likely income. So if you happen to know that it's a school teacher and a Dunkin' Donuts employee, what you'll be able to do is go look up some sources of authoritative information from the internet that can show you roughly in the given geographical area of the house. So that's the other variable here. It's location. And you can get micro-targeted on that location all the way down to the neighborhood if you can. And then also the specs of the house, square footage, number of bedrooms and bathrooms, etc. So you'll try and get as much information as you can out of this, the episode that you watch. First of all, about the buyers and how much income you think they're going to be able to make. Second of all, about the likely market value of the house. It's one of the criticisms of house hunters as a show is that they're not always depicting reality, unfortunately. It's supposed to be a reality-based show, but sometimes the houses that they put on there are worth a different amount than what the show claims that they're worth. And likewise, the mortgages that buyers are getting approved for are not necessarily the mortgages that those real-life people may have been able to be approved. There's some artifice that goes into making the show that I want us to kind of try and peek behind a little bit. And so with this information, so you're going to funnel this information together, and from the likely market value of this house, figure out what would the parameters on a reasonable mortgage payment be. And that is going to be an opportunity for you to do an interest calculation, like the one that we did at the end of our last unit. Right? If I know how much the house is worth on market value, and I know some of the specs about a potential mortgage payment. Maybe make a speculation about how much money they're going to put down on the house and so forth, right? What interest rate might they be able to expect that they can get? So we'll draw from various sources of information to figure out about what we think a mortgage payment would be for the house that they identified in that episode, for the house that they bought, supposedly, in that episode of House Hunters. And then secondly, once you know more about the buyers, to figure out what do you think their likely monthly income is, then the question is going to be, what would that potential mortgage payment be as a percentage of this couple's take-home pay, their monthly income? Because as anybody with a large rent or a mortgage payment knows, it's for most people the biggest bite that gets taken out of their monthly budget every month. And so it's really a comparison. This is the kind of part-to-whole comparison that we're going to talk about a lot in probability land. A comparison between the mortgage payment and the monthly income. That's what's going to tell you whether or not this mortgage is a good risk for a bank or not, right? Whether this couple should be expected to be able to get a mortgage that's that large. Because there are generally some guidelines that lenders and banks like to see buyers hold to. Very often, there's kind of a rule of thumb in the mortgage industry that we want this to be 40% or less. Right? So if I make $1,000 in a given month, then according to this 40% rule, I want a mortgage payment that's $400 or less in order for it to be sustainable, because mortgage is only going to be one part of your monthly budget. You still have to pay the bills and put gas in your car and do all these other things that go along with life. And so mortgage lenders over the years have learned if it's more than 40% of your monthly income per month, a lot of people can't sustain that, and it makes you more of a risk. So that's the main question that I'm asking you and your teams to work on as part of this project. Find an episode of House Hunters, watch it, tell me all the demographic information about those buyers. What are their jobs? Where are their jobs located? Do some online research about the kinds of incomes that those jobs tend to make in the areas that these couples or buyers or whoever in the show reside. Right? And from that, be able to boil that down to a monthly gross income. We're going to forget about taxes for now, because mortgage lenders typically do these calculations on the basis of pre-tax gross income anyway. So figure out what their average monthly income for a family in this situation would look like. But of course, since there's variation, one of the things we'll be able to do towards the end of the project is to be able to put a range on that. Rather than saying, well, this couple's average monthly income is probably $3,500. We may be able to get more information such that we can put a bracket on it and say, well, their average monthly income is, there's a 95% chance, for example, that their average monthly income is actually between $3,000 and $4,000. Right? So a range instead of a point estimate. That's something we'll be able to do as we get towards the last few steps in the project. So tell me about the buyer's range of monthly income that they're probably making. and then do the analysis on the house. See if you can infer from the show what's the location of this house, what city, what neighborhood if you can. And then there are real estate sources online where we can look up, well, what do we think that a house of similar specifications, so similar square footage, similar number of bedrooms and baths. This is what realtors call looking at comps. Find me some comparable homes that have similar specs, and what did they sell for? What are the values of those houses likely to look like? Because again, we're not taking the show's word for it on what the value of those houses are. And with that information on the value of the house, figure out what kinds of mortgage payments might be reasonable by doing an interest calculation, choosing some sample interest rates and figuring out if you annualize it over 30 years, so I think we'll use 30-year mortgages as our benchmark here for this project, what would the monthly payment on that mortgage be? And then by comparing that mortgage payment with that likely income range that the house buyers are in, you'll be able to hopefully make a conclusion at the end. Will they be able to afford this house? Will their monthly income be large enough or the mortgage payment small enough so that the mortgage payment can be 40% or less of their average monthly gross income? So that's the fleshing out of what this project is. And I'll talk more as the weeks go on what the final result of this can look like. Ultimately, your team will need to either write up a document which lays out your conclusions and provides the background quantitative analysis, right, the mathematics behind the conclusion that you're making, or you can choose to make it in the form of a PowerPoint or similar sort of slide presentation. You can choose to record it together as a video presentation. This is the really shoot the moon example. If you want to sort of create a screencast of your PowerPoint presentation, that would be great. So there's a variety of different end products, but the end product should be something that you could give to the buyers on that show that can say, hey, look, we know that you, school teacher and Dunkin' Donuts employee, are trying to buy this $1.5 million house, but here are the numbers that back up why that's a bad idea, why we don't think you can afford that house based on the income, based on the value of the house, and based on this 40% benchmark. And then maybe also provide some recommendations. Say, well, you could get into this house if you increased your down payment to this amount. Or you could get into this house if you got an interest rate of such and such. Or you might be able to afford a house that is worth this much money instead, right? So at the end of the day, providing them with that document that shows them whether or not they can afford the house, and if the answer is no, giving them some other options for how they might be able to afford it or afford a similar house. So that's my talky introduction to what the project is. For the students that are in my course this semester, I shared with you a link that goes to my blog that shows more of the sort of the write-up and the individual components that make up this project. We're probably going to hew pretty loosely to the specifics that are there because there's probably more there than we're going to be able to do over the course of 5 weeks. But it sort of outlines what I'm looking for a little bit more in detail there. So that's an introduction to what the project is. And every week when we meet together for these live streams, part of the work we'll do that week is here's the next step to do in the project and how does it connect with the material that we're learning either in the week that we're talking about or in the week that we've just finished. So let's go forward and talk about some terminology and the sort of the lay of the land in how probability and basic statistics is going to work. I'm going to take just a quick half a minute break here and blank the screen, and we're going to come back and start with that terminological and philosophical introduction to how probability works. I need to get out of the habit of muting my microphone when I blank the screen, because I always forget to turn it back on. But it's good to be back. Let me just re-say what I just said that you couldn't hear. So we're going to move forward to talk about probability and statistics. That is the last act of our course. And both probability and statistics are about a similar kind of thinking. It's the kind of thinking that's involved when we want to understand how a small part relates to a large whole. Right? In the case of probability, what a probability is it is a gauge of how likely a small subset of possible things that might happen is to happen, compared to the full universe of things that might happen. That was a clumsy sentence. Let me try that one again. What probability is about it's about looking at a universe of possibilities and asking how likely are a few of those possibilities to occur. Right? That's what a probability is. It's a comparison between a small subset of possibilities that could occur, called an event. It's a comparison of the likelihood of that event to the likelihood of anything at all that could possibly happen, called the sample space. So it's a comparison between the size or the likelihood of a subset of outcomes to the full universe of possible outcomes. That's what a probability is. In a similar fashion, statistics is going to be about making conclusions or drawing inferences on a very large universe by observing only a small part of it. For example, if I want to understand something about all Bridgewater State students, I'm probably not going to go ask all 9,050 of them a question. I'm going to choose a small sample of them that I hope is well representative of the whole student population. I'm going to ask them, and then try and draw an inference to the larger population based on what I learned from my small sample. So in probability, there's an event and its relation to the full sample space. In statistics, there's a sample and its relation to the larger population. Both of those are similar kinds of comparisons of a part to a whole. In the case of statistics, that part-to-whole comparison loses some information. Because after all, we can't know for sure what the whole population thinks. We can get an idea by looking at a sample, but there's going to be an inherent uncertainty of measurement involved in there. And so what that sample thinks is going to form kind of our center point, but there's going to be a whole range of possibilities around that center point of uncertainty that we want to be able to quantify. We don't just want to say we're not sure. We want to be able to say how not sure are we when we extrapolate from a sample to a population. That's what we're going to hope to be able to do with statistics as we get toward the end of the semester. So let's forge straight ahead and start talking about some of the terminology. So some of the goals that I have for our discussion for the rest of today's live stream are, first of all, to be able to understand some of the definitions that surround the usages of probability in particular. So I mentioned a few of these words just a few minutes ago. Words like events, outcomes, trials, mutually exclusive events. I also want to talk about conditional probability and basic probability. So I want us to just develop some understanding of those things because I find it's really hard to understand them without a context, without specific problems that we're talking about or specific real-life connotations that we can be thinking of. That's, for me, the best way to understand what these terms mean, and also drawing pictures, as I always do, to help to understand concepts. So I want to talk about those two things. And I don't know that we're going to get a chance to get quite as deep into this as I would have liked to today, but what you'll notice is that some of the words that we spent quite a bit of time pulling our hair out about back in the set theory and logic unit of the course. Words like ands, ors, and nots, conjunctions, disjunctions, and negations, or intersections, unions, and complements. Those are going to come back to us again in probability theory, because probability theory is at its heart about the process of comparing the sizes of sets. In particular, comparing the size of a subset to the size of the larger set in which it resides. That is what probability is about, for some appropriate meaning of the word size. So that's going to be that's the trick that mathematicians and probability theorists worry about the most, is what can size possibly mean? Most of the time, it's going to mean something that's completely going to be intuitive to us in the problem and in the moment. And I'm hoping that that's going to be the case with the first example that I want us to start looking at. So here's the example. And I'm going to use this example to illustrate the definitions of these various probability terms that we want to be able to nail down. So the first thing to know is the definition of what it means to be an outcome. So an outcome in probability is just something that might happen So if I flip a single coin once, there's two things that might happen. It could land on heads, or it could land on tails. So heads is thought of as one outcome, one possible outcome in that scenario. Tails is thought of as another possible outcome. So outcome is just a single observable thing that might happen when a probabilistic event occurs. And an event is nothing more than a collection of outcomes. It's a set of outcomes. So let's start by thinking about the example that I want to set up for us. So let's consider an experiment in which I take a fair coin. Maybe I have one here in my desk. Or maybe I don't, because I'm broke. Nope, here's a quarter. So I take a single coin. I don't know for sure whether it's what probabilists call a fair coin. I don't know if heads are equally likely to tails. We are going to have to talk a little bit about that in a few minutes. But no matter whether I have a fair coin or an unfair coin, if I flip this coin and let it land, there are two things that might happen, two outcomes. It could land on heads, or it could land on tails, right? And so for a single coin flip, so if my experiment is a single coin flip, there are two possible outcomes. I'm going to write them in green here. There's heads, and there's tails. And that describes for me the full universe of possibilities for what might happen in this single coin flip. And if I take all possibilities taken together as a set, so if I draw a rectangle around them, I give this thing a name, I'm going to call this set S. This set S is called the sample space for my experiment. Sample space is nothing more than the set. So remember, a sample space is a set. It's not a number. It's the set of all possible outcomes. So if we wanted to use our set notation for this sample space, I would just put in curly braces the elements that make up this set, H and T. Right? It's the set of all possible outcomes, and the outcomes themselves are respectively H and T. Meanwhile, inside of this set, which is the sample space, I can look for smaller structures. I can look for subsets. So maybe here's a subset. I'll call this subset E. So this is a subset of my sample space. A subset of a sample space is called an event. So this is a subset of the sample space. So it contains some of the outcomes that are possible, not necessarily all. But again, it's a set. And so this particular set has only a single element in it. It's just the element H, right? So it's a subset of my sample space. It's called an event. And so then the question is, what is a probability? And I've been saying this in words in this video, but now we can make this concrete by giving a formula for it. So the probability of an event E is defined to be, so here's one way of thinking about what a probability is. It's a comparison of the event, which is a subset of the sample space, to the entirety of the sample space. And the comparison is going to be a ratio. It's going to be a division process. The problem is, E and S, the event and the sample space, those are both sets. They're not numbers. And I can't divide one set by another set. I can divide one number by another number. So how do I turn a set into a number? This is the question that probability theorists spend their energy thinking about. Because if you want to get technical about how probability works, that process of turning a set into a number has a whole bunch of different answers to it. There are a lot of different ways of measuring a set and using a number to represent the size of that set. Those are called, in probability theory, they're called measures, or probability measures. And they have to satisfy certain properties in order for them to qualify as being valid ways of measuring the size of sets. But for our purposes, The only measure that we know so far in our course for how to get a number that describes the size of a set, the only measure we have so far is called the cardinal number. And so one way of understanding how to measure the sizes of sets is to take the cardinal numbers and divide them. So the cardinal number, remember, is the number of elements in my set. But when my subset is an event and my set is a sample space, then the elements are numbers of outcomes, because the elements of those sets are outcomes. Right? And so, for example, if I want to know what is the probability of this event, and so far I've written this event using a set roster, but I could also have written this event in English. Let's use that verbal lingo here. This is the event of getting a heads when I flip this coin, right? And the sample space is the event of flipping a coin. Event of getting heads or tails. Right? How many different outcomes are a part of the event, which is the event of getting a heads? Well, there's only one outcome in that event, right? And so that's going to be 1. Meanwhile, in my sample space, there's 2 possible outcomes, H and G. And so we might be led to believe that, quote unquote, I'm going to write this in English again, the probability of flipping a head is 1/2. Right? And that's jives with our ordinary everyday expectation about what happens when I flip a coin, right? But that relies upon an assumption. I didn't state the assumption here because I wanted to have this part of this conversation right now. In order to get a probability of 1/2, I implicitly assigned an equal likelihood to the 2 outcomes, heads and tails, that are a part of my set. When I use the cardinal number as my measure for the size of these sets, using the cardinal number means that I'm assuming that all of my outcomes are worth the same, that they're just as likely as any other outcome to occur. And that's something that is not necessarily always true. And so that's why probability is interesting and often challenging. Right? Is that we have to be able to unpack the assumptions that we made in order to get to the conclusion that we wanted to get. So here's the caveat that I can put here. When all outcomes are equally likely, it is, in other words, when it is just as likely for me to flip a head as it is to flip a tail, which is what we usually assume for coins, because we usually assume that the coins are fair. That's what fair coin means, right? When all outcomes are equally likely, the cardinal number is how we measure the size of a set. Right? And so we don't, in this case, have to overthink. Right? If I have a fair coin, then it means that heads is just as likely as tails. And so how much of the total sample space is made up by this subset? Well, there's just as much probability mass, is what we would call it, inside of the set E as there is outside of it. And so the ratio of the amount inside to the total amount is a ratio of 1 to 2. So the equally likely cases are very nice to work with. Unfortunately, a lot of probability sample spaces, a lot of probability spaces do not equally distribute their probability mass. So to see why that might be the case, I want to actually look at one more example before we get to our 3-flip experiment that will give us an opportunity to talk about trials, let's do one more kind of example here before we move off of this one. So let's suppose that I take as my sample space that I want to roll a set of 2 fair dice. Six-sided dice. So the usual cubical dice that you get with a average board game. Right? Roll a set of 2 fair 6-sided dice, and then record the sum, the total of the roll. Right? I'm going to add up the numbers that are on the 2 dice. So first of all, what is the sample space going to be for this experiment? What is the set of all possible outcomes? So to answer that question, this is the sample space, right? I just have to ask myself, if I roll a set of 2 fair 6-sided dice, what are all of the different things that I could get as the total of the roll? Well, I can get any total from 2 up to 12, right? So I can get 2, I can get 12, but I can also get 3, I can also get 4, 5, 6, 7, 8. I'm going to try and fit this in nicely here. 5, 6, 7, 8, 9, 10, or 11. Right? I can get any number from 2 through 12 when I roll a set of 2 fair 6-sided dice. So that's my sample space. And each of those numbers that I wrote inside in green, each of those numbers is an outcome. Right? So there are my outcomes. And the sample space, remember, is a set. 2, 3, 4, up to 12. Right? Okay. So now let's define an event. Let's define 2 events, E and F. Let's let E be the event of rolling a 2. Snake eyes, they call it. Right? And let's let F be the event of rolling a 6. Now notice, each one of these events consists of a single outcome, right? So E is equal to just the set containing the outcome 2. F is just the set consisting of the outcome 6. So each of those consists of a single outcome. Here's E, and here's F, right? As subsets of my sample space. But are these events equally likely? Am I just as likely to roll a 2 as I am to roll a 6 when I roll 2 6-sided dice? And the answer to that question is no. It is not equally likely. And the reason that they're not equally likely is that there's only one way that I can get a 2 on my dice. One of the dice has to come up with a 1, and the other die has to come up with a 1 also. So there's only one roll that makes a 2. And that's, again, just a 1 with a 1. Meanwhile, to get a 6, I can have a whole slew of possibilities. I can get my 6 from the first die having a 1 and the second die having a 5. That's one possibility. Or my first die could be a 2, and my second could be a 4. That's another possibility. Or I could roll a pair of 3s. Or I can kind of keep going here. My first die could be a 4, and my second die could be a 2. Or, last but not least, I could roll a 5 and a 1. So it turns out there's 5 rolls that are possible. Right? And so for that reason, 2 and 6 are not equally likely outcomes for this experiment. However, what we can say is we can say that these rolls have equal probability to one another. So rolling a pair of 1s is equally likely as rolling a 1 and a 5, which is equally likely as rolling a 4 and a 2, which is equally likely to rolling a 2 and a 4, which is equally likely to a 5 and a 1, which is equally likely to a 3 and a 3. Right? And so if that's true, then what we might think of is we might think of 2 and 6 as actually standing in for a set of different dice rolls. And maybe think of my sample space as dice rolls instead of the total of dice rolls. In which case then I would have a total of 36 possible dice rolls, from a pair of 1s all the way up to a pair of 6s and everything in between. And each one of those 36 dice rolls is going to have equal probability. But then, so that's probably the more fruitful way to think of it, somewhere in the universe I actually have an illustration of that. Let me see if I can find it so that I don't have to draw this whole thing. Chart of dice rolls. So if I can find this, I think this really helps to make the point. But of course, during my live stream, my MacBook Pro slows down to a crawl. So bear with me here while this gets loaded up. While this is loading up, I think what we can say to kind of wrap up this example here, is that F is 5 times as likely. So there's one of those comparisons by division. Right? If I divide the number of dice rolls in F by the number of dice rolls in E, I'm dividing 5 by 1, and so the comparison is F is 5 times as likely as E. So the probability of F will be 5 times as large as the probability of E. Now we don't know yet what those probabilities are, but we can find them. I'm just waiting for, yes, here it is. Here's the chart I'm looking for. Let me just throw it over onto my iPad as soon as it comes back up here on the screen. Uh-oh. Just give me a couple more seconds here because my browser is being slow. And I'll throw this over to my iPad, I hope, and we'll put it on the screen shortly. There we go. Okay, so instead of thinking of my sample space as being the numbers 2 through 12, those are the totals of my dice, we've just established that those numbers, those outcomes, do not occur with equal probability to one another. And so it's probably better to rethink the sample space in a way that does give us equiprobable outcomes, outcomes with equal probabilities as one another. And one way of doing that for a roll of 2 fair 6-sided dice is, why did that not work just now? Try that one more time. No, that didn't do it. Looks like I've got to quickly convert this file to a different file type before I can put it onto my canvas here. Just give me a couple seconds. This visual is worth it, I promise. I mean, for me, this is the diagram that best illustrates what's going on when we're trying to determine probabilities based on a roll of 2 dice. Because it's a total, like I say, it's a rethinking of what the sample space is, what it represents. So rather than thinking of the sample space as being numbers, I want to think of the sample space as being dice rolls. And when I think of the sample space as being dice rolls, here's what happens. Whoops. Oh, I get it. So here's what the new sample space looks like. So my new sample space is made up of rolls of the dice rather than of numbers, right? And now the sample space has 36 elements in it. And the elements are rolls of the dice. So starting from 1 and 1, going all the way up to 6 and 6. And the cardinal number of the sample space is 36. Right? It's the number of different dice rolls that are in my chart over here. That's my new sample space. And now my outcomes are dice rolls instead of totals. Right? What this also requires me to do is to rethink how I define events. Because now, event is still a subspace of my sample space. If I look at the event of rolling a 2, let me color code this so that we can see what we're doing best. Let's color code this event E. Oops. Let's color code it blue. It no longer consists of a single outcome, which is the number 2. But when I look in this sample space, E consists of a single outcome, which is this one roll of the dice that gives me 2. So the event E now is this subset. And the cardinal number of E is 1. There's only one roll of the dice that gives me a total on my roll of a 2. Right? So that's my one event E. Meanwhile, what about the event F? So F is the event of rolling a 6. It's, again, no longer made up of an outcome, which is a number. It's made up of a set of dice rolls, namely the set of dice rolls that correspond to the total of 6. And I find those as a subset of my sample space, but now it's a large subset of my sample space. It has 5 different outcomes in it. These are the 5 that I was talking about a few minutes ago. Right? So the subset of the sample space that consists of all 5 of these outcomes, that is my event F. Here's F. And the cardinal number of F, the number of outcomes that make up F, is 5. Because there's 5 different rolls of the dice that are possible to give me a total of 6. Now, again, why was this shift in perspective useful? It was useful because now I'm looking at a sample space in which I know about the probabilities of all of these different dice roll outcomes, because all 36 of these events have equal probability to one another. That was the point of rethinking what the sample space was. All 36 are equally likely. It is just as likely that I roll a 1 and a 1 as it is that I roll a 6 and a 3, as it is that I roll a 4 and a 6, or a 5 and a 5, right? All of these are equally likely to happen. And so because they're all equally likely to happen, I can use the cardinal number of these events, these subsets, as my way of measuring the size of sets. Because cardinal number doesn't care about whether some elements might be bigger than others, whether some events might be likelier than others, because it assumes that all of the outcomes are equally likely. So we can ask the question, what is the probability of the event E? In other words, what's the probability of rolling a 2? In its notation, we call it P parentheses E, P of E, probability of E. And again, we get it by dividing to make a comparison between the cardinal number, the size of the event E, and the cardinal number, the size of the whole sample space, S. And as we just decided, rolling a 2 is an event whose cardinal number is 1. My sample space, all possibilities, 36. And so the probability of the event of rolling a 2 is the fraction 1 over 36. And if we want to, and in a lot of contexts we do want to, we can convert that fraction into a decimal and convert that decimal into a percent. This is something that, of course, we would borrow some technology in order to accomplish. So let's just get that up on the screen real quickly here. Sorry, let me get my window back in action here. Sorry, I've got an error message. Let me just open Desmos and use it as my calculator, because why not? I like to give Desmos as much free publicity as I can, because it's an amazing free open source graphing calculator software. Of course, it's also super slow on my computer when I'm streaming, because live streaming just cripples this poor MacBook. I think on my list for Santa Claus for next year, I think I want to put a faster computer. Work Santa Claus. 1 out of 36. There we go. So as a decimal, we have 0.02777 and so forth. 0.027, I'll just round, 0.278. And of course, if we wanted to report this as a percentage, and this is how most probabilities in popular culture get communicated. I'm thinking even of the TV weather forecast. They don't report this kind of stuff as often as they used to. But there used to be a lot of weather forecasts that'll say 30% chance of rain, that kind of thing. Same story. Those are all probabilities as well, and so they get reported as percentages very often. 2.78%. And so there we have it, right? The probability of rolling a 2 on a pair of 6-sided dice is 2.78%. And we tend to think of that's how likely that event is to happen. And then real quickly, let's compute the probability of F as well. Probability of F. Likewise, again, because all of my outcomes are now equally likely, I can use the cardinal number of these sets as a proxy to measure the probabilities. It's the cardinal number of F divided by the cardinal number of S. That divides how many different outcomes give us a total of 6 on my dice, divided by how many different outcomes are possible in general. Well, there are still 36 outcomes in general that are possible, but of those 36, 5 of them are part of the event that I'm interested in. So now my probability is 5 out of 36. Which, again, we can pull up a calculator and get a decimal, 13.88, and so forth. And I'll just change that directly into a percent. We'll just call it 13.8% for now. And again, the observation that this is 5 times as likely as that is borne out, right? If I divide this number by that number, sure enough, I get the number 5. So it's 5 times as likely that we roll a 6 as it was that we roll a 2. So that's the basic lay of the land in what probabilities are. They're a comparison between a subset, which we call an event, to a whole, which we call a sample space. Right? How much of the sample space does that event comprise? But of course, the tricky part is that in order to answer that question, we have to know how to measure the sizes of those sets. And when all of my outcomes are equally likely to one another, that's a straightforward thing to do. When they're not, we have to think a little bit more about it. And in this case, that led us from the first idea, which was to just have my sample space be the numbers 2 through 12, into reconceptualizing the sample space as being made up of dice rolls instead of being made up of numbers or totals. All right, so I want to finish up by talking about just 2 more items of probability terminology that we didn't quite get to. And I don't want to do as much with these because we're going to have plenty of chance to do more with them later. But I want to talk about what it means for events to be mutually exclusive, and I also want to talk about what conditional probability is. And I want to do it on the backs of my same dice roll sample space as we had before. So again, let's consider a sample space that consists of the different rolls of a pair of 2-sided or a pair of 6-sided dice. So here's my full sample space. Now let me define 2 events. Okay, once again, just like we had before. Let's color code one of those events in blue. Call it K. Let's let K be the event that the total on the dice is, I don't know, less than 5. Okay. The event that the total roll of my dice is less than 5. So inside of my sample space, what subset makes up that event? Well, all I have to do is look for the outcomes that belong to this subset. The outcomes for which the total on the dice is less than 5. Well, if the total on the dice is 2, that's definitely a part of my event. If the total on my dice is 3, that's a part of my event. And if the total on my dice is 4, that's a part of my event. But if the total on my dice is any larger than 4, then it's not a part of this, right? Because 5, a total of 5 is not less than 5, and certainly anything bigger is not going to qualify either. So if the question is, what does my event look like as a subset of the sample space, it's these outcomes up here, taken together as a set. So there is my event K as a subset of my sample space. Now let's define a second event. Let's let L be the event that one of the dice came up a 6. Right? So one of the dice that I rolled happened to have come up a 6. If I go into my table, I can find all of those outcomes as well. Let's say the event that exactly only one of my dice came up 6, just for fun. So let's shade those outcomes in my table. My 1 and 6 roll is such an outcome. My 2 and 6 is an outcome. 3 and 6 is an outcome. 4 and 6, 5 and 6. But because I added the word exactly here, 6 and 6 I'm not going to include, just by what I've written down here for the definition of my event. So here's 5 of the outcomes that make up that set. But there's 5 other ones as well, right? They're over here. 6 and 1, 6 and 2, 6 and 3, 6 and 4, 6 and 5. And so those outcomes, taken together as a set, form a subset of my sample space, which we're calling the event L. So let me just draw a lasso around all those. There's my set L. My event L, sorry. Right. Okay. So what's the first thing that you might notice about the relationship between these two sets? Well, there's no outcome that belongs to the set K that also belongs to the set L, and vice versa. There's no outcome from the set L that also belongs to K. So K and L have no outcomes in common. If one of these events occurs, the other one cannot occur, because there are no outcomes that reside in both sets. And the terminology that we use for this is we call the events mutually exclusive. Right. And since we know this terminology from the first unit of our course, the way that we could express mutually exclusive using sets is we can say the two events are mutually exclusive when they are disjoint as sets. In other words, when their intersection is the empty set. So that is what mutually exclusive means. If one of these events happen, the other one cannot happen, right? Because there are no outcomes that are common to both of these two events. So mutually exclusive just means that these cannot occur at the same time. There's no outcome that belongs simultaneously to both sets. And finally, let's talk about conditional probability. And the way that I want to do that is I want to keep my event K, but I'm going to delete my event L for a minute. So let's get rid of L. Just give me a second to get all that orange off of here. There we go. Okay, so I'm keeping my same event K, if I were to ask you, what is the probability of k? What's the probability that the total on my dice is less than 5? Well, again, because all 36 of these outcomes are equally likely, I would take the cardinal number of k, divide it by the cardinal number of s. Cardinal number of k is 1, 2, 3, 4, 5, 6. There's 6 possible outcomes. Cardinal number of the sample space is 36, so it's 6 divided by 36. It's the same as 1/6 as a reduced fraction. It's the same as 16.67%. And that would be the probability of k. But I can also ask about probability by changing the sample space as well. I can shrink down my sample space. And here's what I mean by that. This will be our last example for today's live stream. I can shrink down my sample space by restricting myself to another subset of the events. So let's suppose that L is the event that my first die, the red die, is, let's let L be the event that the red die is a 2. Right? So the red die comes up 2. That gives me an event that I can talk about. And inside of my table of possible outcomes, my sample space, I can highlight, here's the subset of elements that make up that event. Let me try and shade them also, as long as this doesn't get too confusing. Right? So there is my event that I'm calling L. Right? So rather than ask for the probability of k on the whole, I might have the occasion to ask about what is the probability of the event k happening on a smaller sample space. This, by the way, is sometimes called Bayesian Inference. It's how human beings learn about the world around us in a lot of ways, right? Is that we have a preconceived notion, think of that as a probability, and then we get some additional information that helps us to shrink down our universe of possibilities a little bit, and then we reassess that old probability in light of a new, smaller sample space, a new, smaller set of possibilities in the world. As we learn new facts, the number of possibilities of different outcomes that could be true shrinks. Right? That's in a sense, as we search for truth, we're shrinking the universe of things that we believe might actually be in the realm of possibility. It's a bit of a paradox of learning, right? It's sometimes called Bayesian inference. And so what I can ask, and I'm going to very carefully ask this question, is given that the red die came up 2, what is the probability that the total is less than 5? So that's a new kind of question. That the total is less than 5. And the word given is a giveaway. When we talk about this topic, we tend to use words like given a lot. So given means that no longer are we going to consider all of the events in my sample space anymore. I'm only now going to consider those events in which the red die is 2. So my sample space effectively shrinks. I get rid of all of the outcomes that are outside of my event L. So I wipe those out, I wipe this out, I wipe out my first row, and my new sample space is smaller. Now all I have to do is divide the number of outcomes in my event by the number of possibilities, but the number of possibilities is smaller. It's the size of L now instead of the size of S, and now the number of events in my new sample space is actually the intersection of K and L. 1 out of 3. We call that a conditional probability. So a conditional probability is what you get when you have some information that lets you revise your sample space, and then you consider the new probability in relation to that new sample space, throwing out everything which is outside of the new sample space and just narrowing your focus. So we're going to have a chance to talk about a lot more of this in much more depth as we go over the course of the next couple of weeks. I look forward to working on that with you, as well as on working on our project with you, and I'll see you in our class.